Okay, that's all set. And it's 3 o'clock, so I will start the webinar and just watch the people come in.
All right, hello everybody, and welcome to the second to last session of the conference. We are looking forward to starting it in just a few minutes. I'm waiting for people to get on. It looks like the numbers are coming up. I hope everybody's been having a really good conference. I know I have been. And so, okay, I think it's now about time to begin announcements. And so I am going to start by sharing my screen. And I just want to I'm going to start off with a little thank you. I want to thank everybody who participated in the voting process. Now is time to unveil the decision that we have as a community have made. And before we start that, I just want to say a quick thank you to everybody in the community for participating. This has really been an effort of lots and lots of people. It was really Fernanda Ferrera's idea originally to start talking about a society. That began 3 years ago at the Davis CUNY, and then we had a committee that Sarah Brown-Schmidt organized, and a bunch of people were on that. And then there were a bunch of people on some more recent committees. And of course, the business committee has been very involved all along. And most recently, I want to thank Miran Edelstein, who works in Vic Ferrera's department at UCSD, because they really volunteered their time there to help us make the vote actually happen. So now over to Tessa Warren, who's going to tell you what the outcome of the name vote was. Tessa, we can't hear you.
Sorry about that. So for the past 34 years, our community has met annually for the CUNY Conference on Human Sentence Processing. The inclusion of CUNY in the name recognizes and honors our founders, Janet Fodor and her colleagues at CUNY, and the critical role that they played in nurturing and frequently hosting the conference, especially early on. In all, they hosted the conference 10 times. Unfortunately, over the past few years, it has become clear that there are problems associated with having our conference name tied to the CUNY institution. These include making it more difficult to secure funding from local host universities and competition and confusion on social media. So with the blessing of our CUNY colleagues, we formed a renaming committee. The committee included me, Janet Fodor, Tom Wassow, Tamara Swab, Amit Elmore, Daphna Heller, and Ava Wittenberg. We solicited suggestions for new names from the community last spring and used them to develop the ballot that many of you voted on earlier this week. So we've now counted the vote and discussed the issues that were raised in the comments on the ballots. Thank you everyone who contributed concerns and thoughts. So there was a clear winner, and it was the 10th Annual Conference on Human Sentence Processing. So the name of next year's conference will be the 35th Annual Conference on Human Sentence Processing.
Yay!
Woohoo!
Yay!
So a few things to note. One is that it happens to be the case that this name is what you get if you simply drop CUNY from the current conference name. And two, that we recommend that it be abbreviated to HSP year. So next year's conference would be HSP 2022. But of course, change is slow, and we all might continue informally calling the conference CUNY for a while. Thank you.
Okay, all right, thank you very much. And so along with that, I also just want to quickly announce that there was overwhelming support for starting a society. It's not going to be a legal society, at least not at the beginning, but it's going to provide some organizational support for the local committees that are putting on the conference every year. And it's just named after the conference, so it's going to be called Society for Human Sentence Processing. And we have a website that we created actually about 3 years ago, and it is almost ready to go. We've just got a couple of tweaks, and I will be sending that out before the end of the conference, so that you'll be able to go and look at it live. And so at this point, we just have a couple other quick thank yous. And so I'd like to turn it over to Colin Phillips for a thank you.
Thank you. John, is Janet on and you're able to bring her in?
Let's see. Ah, yes, there's Janet now. And if Janet, you can unmute if you wish. I can ask you to unmute.
I'll do what I'm told.
Yes, great.
Okay, as we start this new phase, there's going to be a process to form an executive committee that will lead the new society and will put the conference on a firm footing for years to come. And when you voted to approve the society, you also voted to approve a process for creating the initial leadership team, which is going to unfold in the coming weeks. But one of the leadership roles is past president, and that's kind of hard to fill for a society that's only just starting. But in this case, there's a perfect solution. So I'm happy to announce that the first past president of the Society for Human Sentence Processing is the person who set everything in motion 33 years ago. And that person, of course, is Janet. So,
Yay.
Can I say thank you?
Yes.
And I want to say it's wonderful to be a past president without having had to be a present president. And the second thing I want to say is that I'm about to practice playing golf.
So I wanted to say a bit more and just in sort of appreciation of what Janet has done. So in the past year, we've had lots of opportunities to think about things we've taken for granted. And it's easy to take for granted what happens at this conference, but that wasn't always there. And what we have today strongly embodies the vision that Janet had when she organized a smallish meeting for some kindred spirits at CUNY Graduate Center in 1988. So Janet's vision was to get people together and get them talking across fields where you could have people drawing on psychology, linguistics, computer science, maybe a little bit of philosophy too, without really worrying too much about disciplinary boundaries. And the mixing was very much intentional. The conference has always had a single plenary track, even as it's grown larger, to ensure that people would stay together and keep talking with people from different backgrounds. And Janet's vision for how we talk to each other, how we engage across fields is very much imprinted on the conference that we see today. I don't know how far Janet expected this to go or how much she expected it to grow, but I think we can see now that her vision has been realized many times over. So of course she created a conference. As we know that CUNY hosted it 10 times. It then grew to travel the country, and probably she couldn't have imagined that it would be the kind of worldwide gathering that we have now, because in 1988, we were only just starting to hear about email. But it created so much more. It created a field. It has a professional society now, so it must be a thing. And you can see in the presentations this weekend, there's so many individual presentations that bring together sophistication in linguistics and psychology and computation in ways that probably seemed like a bit of a pipe dream 30 years ago. And it created a community. There's hundreds of people who don't only come together for one weekend every year, they also keep doing science year round, all the way around the world. I'm sure it's helped to create many careers, and it's even created some lives. That sounds extreme, but I actually have direct knowledge on that one. 30 years ago, when the conference first went on tour to Rochester, I was a fresh-faced young exchange student, and I got involved in helping with the conference. I wasn't particularly interested in sentence processing at the time, but I was particularly interested in the grad student who Tom Bever, who had hired to organize the conference. Well, Andrea and I will have been married 25 years this year, and our kid is a freshman in college. So there's at least one person who probably wouldn't exist if it wasn't for the CUNY conference. And I wouldn't be surprised to learn that there are more people out there. So thank you, Janet, for all that you've done so far. And thank you for agreeing to be the inaugural past president for the Society for Human Sentence Processing.
Thank you. Thank you.
All right. Thank you, Colin, for that wonderful that wonderful tribute. So we have,
Thanks, Janet.
yeah, and thank you, Janet, echoing what Colin said. Thank you so much.
Thank you.
And by the way, I'm in this field because of a paper of yours that I read when I was in graduate school, and it inspired me to do my second qualifying paper, and here I am. So we have one other thank you, Al and Jared.
Hi, can you guys hear me?
Mm-hmm.
This is actually an announcement. Jared and I have been collaborating on some really important research on syntactic ambiguity resolution. we have produced the discovery that the following sentences are easy to process. Hit me. There's your sentences. The conference organized by Truesdell and Company was an unambiguous success. John put the conference on Zoom into the record books. Next slide, please.
All right, thanks.
All right.
Thanks,
Thank you, John.
everybody.
Yeah,
Okay.
thanks, John.
Okay, so we need to keep going with more interesting talks, again, on these very same issues of crossing interdisciplinary boundaries. And so it's actually a great pleasure now to let Jennifer take the reins and introduce our first invited speaker.
All right, thanks, John. And so we are now really going to start the second to last session. And it is my enormous pleasure to introduce Chris Manning. I've actually known Chris for so long that I think I know him. I've known him for longer than any other single person at this conference because we were in graduate school together. And so Chris Manning is a professor of both the linguistics department and computer science department at Stanford University. He is also the associate director for the Institute for Human-Centered Artificial Intelligence. And he is an award-winning researcher. He specializes in computational linguistics and artificial intelligence. And he's a leader in the field in the application of deep learning to natural language processing. And right now, I'm very happy to introduce Chris to give one of our invited talks. Take it away, Chris.
Thank you very much, Jennifer. Okay, let me share screen. Okay, share. Okay. Okay, hello everyone, I'm Christopher Manning. So in my talk today, I'm going to be one of the interdisciplinary people who's not really talking about psycholinguistics, human language acquisition and processing, but I want to provide some food for thought from computational linguistics that I think is eye-opening and highly relevant in considering possible theories of human language acquisition and processing. I'll provide both a general perspective about what has happened recently and a bit more depth about two pieces of work that I've been involved with. My topic today plays out some of the more recent episodes of a drama series that is now in its 70th season. Starting in the 1950s, Noam Chomsky developed and argued for an articulated syntactic deep structure for language, and in particular argued against any utility for work proceeding from the frequency of linguistic units in speech or text, saying, but it must be recognized that the notion of probability of a sentence is an entirely useless one under any known interpretation of this term. In contrast, at the same time, Claude Shannon was developing information theory. This not only underlies us being able to video conference today, but he argued that anyone speaking a language possesses implicitly an enormous knowledge of the statistics of the language, enabling them to complete an unfinished phrase. And this is a perspective that has proven to be incredibly useful in psycholinguistics as well as in engineering. In 2018, the world of natural language processing was transformed. The key to the revolution was the use of neural language models. To understand that recent work, let me first quickly introduce the concept of a language model. A language model is a term of art in computational linguistics, meaning a model that predicts a word in a context. So we have a context like the students opened there, and we could think of words that might come after it. Books, laptops, exams, mines. And a language model assigns a probability to how likely words are in this context. So there might be a 4% chance of the next word that comes as books. Language models are a key part of decoding tasks like speech recognition and spelling correction, and they're used in any language generation task, including machine translation, summarization, and story generation. Language models have been around ever since probabilistic methods proved their power for speech and language processing in the 1980s. In the 20th century, we used for language models n-gram models, which were essentially what was proposed by Shannon in the 1950s. So if we want to get estimates for the students open their books, what we do is we get a big pile of text and we count up how often the students opened their books. Maybe that occurred 11 times. We count up how often the students opened there occurred. Maybe that's 187 times. And we can simply divide through and say that the probability estimate is 6%. This is a problematic thing to do because this is a classic curse of dimensionality scenario. Even if you take a vocabulary of only 100,000 words, since we've got 5 words there, that means we're at 100,000 to the 5th, which is the kind of number that's well more than atoms in the universe. And indeed, if you look at Google Books, like that little graph I've got on the side, you can see that according to their corpus, there are whole years that go by without a single occurrence of the students open their books being recorded. And so people did a lot of work on dealing with this problem, limiting context with a Markov assumption, discounting, back off, etc. But nevertheless, even these very simple models were just amazingly useful in computational applications. So if you have a 1-gram model, that's just using the frequency of words. So here's a language model built over Shakespeare. And so that sort of produces for you junk, to him, swallowed, confess, here, both. But even if you just go up to a 3-gram model, you start to produce stuff that starts to sound like Shakespearean English. Fly and will rid me these news of price, therefore the sadness of parting. So linguists started to look at these models and see what they thought of them. And basically, they didn't think much of them. And people argue that they didn't really know anything about the intricate structure of human languages. So n-gram models clearly know quite a bit of simple world knowledge. They know that ships sail and sink and are anchored. And in some unaggregated way, they know some low-level syntax. They know you tend to get sequences like preposition, article, noun, article, adjective, noun, but they only have facts about individual words. They don't know anything about the concept noun or anything about sentence structure rules. They don't have any sort of abstracted grammar whatsoever. And so more knowledge of language seems necessary to understand language. And so in natural language processing in the 1990s and 2000s decades, the completely dominant way of accessing the structure of human languages in systems for various downstream tasks involving meaning interpretation was building context-free grammar or richer parsers for the hand-annotated morphosyntactic resources that display linguistic structure. That is, tree banks such as this parse tree from the Penn Tree Bank. In an abstracted sense, these tree banks validate Chomsky's belief that knowledge of language cannot be gained just from exposure to a lot of language use. However, the 2010s saw the rise of a new generation of neural language models, actually first pioneered in the 2000s decade by Yoshua Bengio and colleagues. These new models solved the curse of dimensionality. They represented words by low dimensionality real number vectors, which allowed sharing of strength between similar words. And then soon after that, they solved the failure to exploit long context via recurrent neural networks. So here's a nice example from a short story of Arthur Miller. If you want to have a guess in the chat, you can suggest what word comes next here in this context. But looking at this context, you can't possibly get this with the kind of n-gram Markov models that were used previously, because if you look at he refused to have, you might think an operation, examination, I don't know. You could look at a really long context beyond what we could do with n-gram language models and think a guest in the past 30 years and which he refused to have, maybe over to dinner or something like that. To be able to guess what is the right answer here, you really need to look way back to be seeing the stump. And if you've looked that far back, you've maybe been able to guess that the next word that comes here is removed. Now, to just give you a bit more sense and detail of what these new models were like. So the first idea was representing words in this initially somewhat strange manner as a real valued vector. My vectors here only show 9 dimensions. Typically, really, people are using somewhere between 100 to 1,000 dimensional numbers for each word. But these representations place each word into a moderate dimensional vector space. And if we zoom into these vector spaces, that we can see these vector spaces capture a lot of elements of word syntax and meaning, so that you see similar words grouping together in a different part of the space that you see all the verbs. And you not only just have a jumble of verbs, their positioning is also representing having the auxiliary verbs in the bottom right, other copular predicate-taking verbs like remain and become very close to be. Down in the sort of left lower, you get the verbs of saying and thinking, expecting that take that complements. A lot of detail is being captured. And then for an RNN, a recurrent neural network language model, what we're doing is we have our context, the students open there, and for each of these words, we're looking up their word vectors. So these word vectors we learn automatically from a large amount of text by trying to predict words in the context of other words. A fully automated algorithm. But then in the recurrent neural network, we have another layer of hidden vector structure where at each time step, we take the previous hidden vector and the word embedding for the next word, do some matrix algebra computations, and predict a next hidden state going along. And then we can use these hidden states to predict what the next word will be. So on top of that, we'll do another bit of linear algebra, softmax computation, which will give us a probability distribution over next words. And this is the basis of the kind of neural language models from the previous slide. But something interesting has happened here that I'll come back to as the central part of the second half of the talk. Now we don't only have word vectors for a word type, but we have hidden word vectors that represent a token, a word in context. So this hidden vector here represents the word opened in the context of the students. But first, let me dive in and tell you about a bit of work that is then telling you about how RNNs can generate bounded hierarchical languages with optimal memory. So in human languages, you get hierarchical structure or recursive structure with nested dependencies. The man that the woman likes left, where it's the woman that likes and the man that's left. Now, it's well known that this kind of center embedding becomes almost incomprehensible as soon as it becomes a little bit deeper. So the man that the woman that the child knows likes left has exactly the same kind of structure as the previous example, but embedding one level more, it sort of seems unprocessable by a human being already. But that's not quite true, because actually it's then been shown by various people, including Jeffrey Sampson, that you do get this level of embedding, providing you have a bit more structure and context. So here's an example from Pulley Blank. The only thing that the words that can lose D have in common is apparently that they are all quite common words. Or from Richard Feynman's Nobel Prize address, the odds that your theory will be in fact right and that the general thing that everybody's working on will be wrong are low. So these have exactly the same amount of embedding as my triple question mark example, but now they seem perfectly fine things to say or write. And in particular, note that people correctly handle this embedding, and so that they get the agreement of the only thing is, or the odds are, across those two levels of center embedding, and that they aren't usually, occasionally they are actually, as psycholinguists have shown, but usually they aren't distracted by the intervening singular nouns. So we could conclude there's definitely hierarchical structure in language, and you actually get it a bit more deeply than you might at first think. But clearly there is a depth bound to what humans can produce and comprehend. So what should we make of this? I mean, actually, in the first half of the 2010s, when I began actively working with neural networks again, I thought the thing to do was to start to explore how you could put neural networks into tree-structured models. And so I worked a lot with students on tree recursive neural networks. A whole bunch of other people took the same goal and did it in another way. It's well known in formal language theory that the other way in which you can get hierarchical recursive structure is to augment your model with a stack. And so a whole bunch of people worked on stack augmented recurrent neural networks. But we then had these amazingly successful recurrent language models. And so we had this apparent contrast where on the one hand, human languages have hierarchical or recursive structure with nested dependencies. But what we found was Rnns, which are simply sequence models, they take one word at a time, they have a sequence of hidden states that represent what's coming next. They turn out to perform well on syntax-dependent prediction. So if you ask questions like, after the chef who made the pizzas, should you have is or are? Neural language model is very good at telling you that the answer is is. And in general, they seem pretty good at representing hierarchical structure. Here's a kind of a fun example. You can get them to generate your LaTeX source code for a random paper, and they know how to close the different blocks so you get a well-formatted paper. So what are the results on the expressivity of recurrent neural networks? Well, on the one hand, you could think this isn't surprising at all, because back in the early 90s, Siegelman and Sontag proved that Rnns can do anything. They're Turing complete. But they did that under a couple of assumptions, that they assumed that you could have an infinitely long recurrent neural network, not one like we've been actually working with. And they also assumed that the real numbers were Platonic real numbers that had infinite precision. But actually, the way everyone uses neural networks in natural language processing is that your neural networks only have one hidden state per token of the input. And more recently, Weiss and Merrill showed that under that restriction, that Rnns or LSTMs can't recognize stack requiring languages. So that would suggest that they shouldn't be performing as well as they do. So for the work we wanted to do, we wanted to tie our hands behind our backs even more tightly, because Weiss and Merrill still allowed the precision of the numbers to grow with the length of the sequence. But that's not what we get in any of our computers. Our computers use fixed finite precision approximations to floating point numbers. So what can we do if we have an RNN with finite precision and one hidden state per token running time? Well, it's obvious that we can't in general recognize context-free languages. Merrill had already shown that. But it seems like the interesting question, given human languages and human behavior, is can RNNs handle bounded hierarchy? So the Dyke K family of languages is a family used in formal language theory quite a bit, which is the language of nested parentheses of multiple types. So if you have parentheses, square brackets, and curly braces, and you make them balanced, you're then using the language Dyke 3. And here I've got an example of then Dyke KM. So for Dyke KM, we add the extra restriction that there's a maximum embedding depth. So in this example, we have a sentence in Dyke 2.4 where there are two kinds of parentheses and the maximum embedding depth is depth 4. Now, what are the facts if you go to Dyke KM languages? Well, because Dyke KM languages require a finite amount of memory because of the embedding depth, they're a regular language. And well, because they're a regular language, it's well known that they can be recognized by a deterministic finite automaton. A deterministic finite automaton with k to the m states In turn, it's well known that RNNs can simulate any deterministic finite automaton, but using roughly the same number of hidden units as states. And so therefore, it seems like, if from what's known so far, that if you want RNNs to generate DikeKM, you might need for your hidden states to be exponential in size. And it's a bad exponential, right? Because again, if we go back to vocabulary of 100,000 words, and well, pulley blank and Feynman could definitely handle m equals 3, that means that we need to be using hidden states of size 10 to the 15, which is kind of beyond what we can do in any of our computers. And so what we did in this work was prove how there was a compact way to encode in recurrent neural networks bounded hierarchical languages. Indeed, with the construction that we made for doing it, that you can handle Dike 100,003 using only hidden units vectors of size 300, which is actually the kind of size that we use in practice. At the starting point, this seems kind of easy to do because, well, since we have a bounded size stack and we have a hidden vector, we can simply say, well, we need to be able to store m things in our stack. So let's just divide our hidden state up into m pieces and represent the things that we have to store in those different pieces, and we're done. But it's not quite that easy, it turns out. Well, we need to be able to push and pop things from the stack. And at first you might think, okay, well, if I've got this vector with these different pieces, I can be clever and come up with a block matrix that I can multiply by it and move things up in the stack. And so therefore I could push something else onto the stack. And I could come up with a matrix where I can multiply and I can do a pop for the stack. But unfortunately, recurrent neural networks don't have this much power, because if you recall the equation for recurrent neural networks, they only just use one matrix over and over. And so that seems like this solution isn't possible. So what we did was came up with a cleverer construction. So in the hidden state, we put 2 copies of the stack, one of which at each complete time step we keep empty. And then we have 2 copies of these matrices for pushing and popping. So we always read from both halves of the vector, we always perform both operations and write them to the 2 halves of our output vector. But then we can use the rest of the construction of a recurrent neural network, that you add on a bias and put it through a nonlinearity to zero out the half of the stack that we don't want. So we can then return to a stack state where we keep one half of the stack, and then we can repeat this over at the next time step. And what we find is we don't know whether actual trained recurrent neural networks use our construction or something similar to it. That'd actually be something interesting to investigate. But empirically, if you try and train recurrent neural networks, that you cannot get recurrent neural networks to learn DikeK in general because of its unbounded memory requirements. But if you restrict things to DikeKM, it is learnable by an RNN of the size our theory suggests. So here we're showing some training where if you're looking at, say, Dike 128.5, that if you train a model on 20 million tokens of Dike 128.5, then the recurrent neural network is able to almost perfectly learn it. So the takeaway here is that we maybe need to rethink the interesting language classes to study. The Chomsky hierarchy places all finite memory languages in the same class. But most neural networks we use have finite memory, as do humans. And it's not actually very useful to just say all of those things are in the class of regular languages. We need finer-grained theoretical tools like memory efficiency to actually understand what kind of languages we should be able to expect to be able to recognize and not recognize. But at this point, I should get back to my main story. In 2018, NLP was transformed by the use of very large language models. These recent deep learning language models are simply artificial neural networks made very large and trained in what's now often called a self-supervised fashion, meaning we take a lot of text, we mask out some words, just like as in a closed task, and we try and predict them given a given context. Once fine-tuned, these models were found to be able to be used for all sorts of tasks, whether it's machine translation, question answering, to perform much better than any NLP systems that had previously been built. The first ones of these models, Elmo and OMFIT on the left, they were big recurrent neural networks, or at least at the time they seemed big. But shortly after that, people started exploring a new architecture for neural networks, transformer models, which you were able to make much, much bigger, essentially because they could be run much more efficiently on modern GPU computers. And so people started building models that first of all use billions of words of training data, then tens of billions of words of training data, and now hundreds of billions of words of training data, models trained for very large amounts of computation time. But the result was that these models just had amazing knowledge of language. Here's an example of the GPT-2 language model. So the style of what's happening here is a human being is writing a beginning of a story. A train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. And then the language model is just generating words, one word at a time successively, like I showed before, to then start to tell a story. And so it says, the incident occurred on the downtown train line, which runs from Covington and Ashland stations. In an email to Ohio news outlets, the US Department of Energy said it is working with the Federal Railroad Administration to find the thief. And so this is just amazing. I mean, not only are these sentences just impeccable, the kind of sentences a human being would write, but they're not only syntactically correct, they're telling a coherent discourse that builds as the story goes on. And in this discourse, it makes a lot of use of the input in a sort of a sustained following along the topic, not doing something weirdo and unexpected. So in the beginning, there's a train and nuclear materials stolen, and it builds from that. It starts talking about Ohio news outlets, because Ohio is in Cincinnati. It knows that the Department of Energy is responsible for nuclear materials. It talks about the Federal Railroad Administration, a thief. It's just a completely coherent, good discourse. For other kinds of tasks, the way these models were used was that, first of all, we do what's called pre-training of the language model. We do these closed tasks of predicting words and try and train our model to predict words and sentences. And then if we have a particular task in mind, like question answering or finding person names in text, we then take some data, which is supervised data, hand-labeled for a particular task, and we fine-tune our language model to be good at that particular task. And this has now become the new normal, right? If you're building natural language processing applications in industry, essentially this is the formula you use for everything, and it works incredibly well. To give you just one example of that, one more thing first. I'm not really going to have time to explain transformer language models. They're pretty complex, but just to give you the slightest idea for what happens later. So when you have a word, you start off with a representation that's like a word vector, but from this representation, you then project as linear transformations 3 matrices, a query key and a vector. And the style of computation they use is from the query, you then look at all other words as keys and your own, and you calculate a score as to how much to attend to the different words in the context. And based on these attention scores, you compute a weighted sum of the values, which becomes a new representation for committee. But you don't just create one representation, you do this, say, 12 times with different queries and keys, and then you combine them to create a new hidden representation for the word committee. And then you don't stop there. I don't show it all apart from this black arrow on the left edge, but you repeat this whole process a whole bunch of times, getting new layers of representation that get more contextualized and abstract away from your original sentence. Yeah, so these models were just super, super successful for all tasks. So a task that's been worked on a lot is question answering, where you have a passage like this one, and the question is, which team won Super Bowl 50? And so as people who made it through the SAT exam at some point, I presume you can look at this text and come up with what the right answer is. Hopefully you can work out that the answer is the Denver Broncos. So for this particular data set squad, the performance that you got from conventional machine learning systems of the kind that everybody used for question answering until about 2014, it could get about 51% on these tasks, compared to mechanical Turkers get over 90 when they do it. As soon as people started using neural systems, you started getting better results. So around 2017, people were getting numbers in the 70s, heading up to the high 70s. But once these transformer models like BERT were invented, the numbers got way better again. So 2 years later, in 2019, you couldn't get on the leaderboard unless you were using BERT, and different variants of the BERT model were now getting results in the high 80s. And indeed, in the 2 years since then, there are now numbers from even larger transformer models that exceed the performance of at least mechanical Turkers, though we might assume that a bunch of academics might be able to score a bit better on this test. Okay, so what I then want to talk about a bit in this second piece of work is to show that these big transformer models actually learn linguistics, despite the fact that they're given this very simple closed task of predicting a masked word. Once you have a large enough high parameter model, the model figures out for itself. Remember, it's trained in a completely unsupervised way. It's just given this task of predicting words in context. It figures out all by itself that it can do this task better if it starts to learn about the sentence structure and meaning of sentences. And so these models discover syntactic structure based on a lot of training data. So how can we...
Chris, that's 5 minutes.
5. Okay, go for it. Okay, well, how could we do this? Well, the first thing is there were all of those attention heads. And so we can look at, for each attention head, what does it attend to? We could see if those attention heads seem to be learning linguistic structure. And we find that they are. So if you look at the low levels of the model, so the first and third levels of the model, the attention heads are doing very simple things. They're doing things like looking at everywhere evenly, just kind of creating a bag of words, which makes sense just to see what's in the sentence. Or they'll look at the word to the left or the right, which sort of makes sense. That's the most relevant first place to look. But once you get deeper into the higher levels of the model and look at what the attention heads are doing, you find that there are very linguistic attention heads. So one thing we can look for is syntax. In particular, we can think of dependencies. So you can think of, well, does a subject look at its verb, or does a verb look at its subject? Does a preposition look at its object? And so we can see if the attention heads are doing the same things that we can see in a dependency tree. And yeah, we find around level 7 to 9 of the transformer lots of heads that are essentially syntactic. So the 10th head at layer 8 is essentially has direct objects, well, actually really the whole direct object noun phrase looking back to the verb. So all of an even harder sell is looking back to considered, specific stocks are looking back to recommending. The 11th head on the same layer has noun pre-modifiers, so determiners and adjectives, and actually also prepositions using an extended projection kind of idea, looking at the head noun. So in the huge new law, in the huge new is also looking at law, the fight, that is looking at fight. Perhaps even cooler, there's a co-reference head. So the fourth head at the fifth level basically learns co-reference. So with Kim as she got some expert opinions on the damage to her home, we find that she here is paying attention to Kim, she, and her. And similarly, you can see her doing the same thing. It's not only pronominal and Afra, joining peace talks between Israel and the Palestinians, and the next sentence, the negotiations are, you're seeing that this same head is showing a tension between talks and negotiations. But that's attention heads. What about these hidden structure representations that these models construct? Do they know about syntax? And so we might wonder whether the hidden representations actually completely capture the dependency syntax representation of a sentence. Well, how might we even be able to discover that? Well, we can discover—
Chris, 2 minutes.
We can discover that by putting a distance metric over both. So trees have a distance metric over them, which is how far apart things are in a tree, the path distance. And our contextualized representations of words at a hidden layer of the model, they also have a distance representation that is just the distance in the vector space. Now, we wouldn't think that the entirety of the encoding was syntax, because a lot of it's going to be semantics and discourse and everything else. So we could want to find a linear transformation of the full vectors that encodes syntax best. And our hope is that if we look in that linear transformation, we could work out tree distances in terms of distances in this transformed space. And in particular, that means that if we just constructed a minimum spanning tree in that space, that minimum spanning tree would recover the syntactic dependency tree of the sentence. And so we set ourselves this task: can we find a single transformation projection matrix, which for all of the sentences in our corpus over all pairs of words can, as accurately as possible, predict tree distance? And it turns out we can do that very well. So simple baselines on plain word type vectors don't really perform beyond a linear tree. But once we go to something like BERT representations, that they're very good at recreating a dependency tree. In fact, if we just look at one example, we see that the BERT's reconstructed minimum spanning tree is almost identical to the human annotated parse tree, slightly off right at the end here. So, the question was, does BERT learn syntax? And we realized that by saying, well, can we actually find the dependency syntax tree and the hidden representations of BERT? And quite surprisingly, we find that the entire parse tree is quite accurately embedded in the BERT representations. So the possible controversial takeaway of this is maybe we don't need to build tree banks anymore. Our unsupervised models can just learn the syntactic structure of text. There's a lot of other work I haven't talked about. There are many other people who've done work studying the behavior of BERT models, including some people who've more explicitly looked at the connections to psycholinguistics. But for my final thoughts, I just want to emphasize again how successful this unsupervised or self-supervised learning of linguistic structure based simply on this closed prediction task has been shown to be. In fact, it seems like what's happened is that with these deep contextual word representations, we've seen a phase shift in behavior from the simple language models of old, so that now we don't just have simple statistical association learners, but we actually have linguistic structure discovery devices. And so to get back to the 70th season of the long-running drama, I think it's interesting to note that distributional learning, this closed prediction task, used so much in modern NLP, it really connects directly to the ideas of the later American structuralists, a period of work that sometimes also actually referred to as distributionalism. So the later structuralists like Swadesh and Harris proposed this idea that there should be discovery procedures for syntax. So in his earliest writings, Chomsky essentially rejected that position and said that it's an impossible goal to build a discovery procedure for grammars that worked from a corpus. But in contrast to that, it actually seems like for the first time now, we are actually in sight of having mechanical discovery procedures for syntax that do just work from a large corpus of text. Thank you.
All right. Thank you very much, Chris. I'm going to clap on behalf of all of the hundreds of people in the audience. We have about 6 minutes left for questions. And we're going to start with a question from Peter Gordon. And am I supposed to unmute him, or is somebody else? How does that happen?
Someone else will unmute.
I unmuted myself. Can you hear me?
Yeah.
Yes, we can hear you, Peter. Go ahead.
So a lot of the power of current NLP models comes from their being trained on a very large sample of language, larger than is plausible as a model of human language learning. Do you think this reflects a fundamental difference in how language is learned and processed, or am I wrong about the amount of training, the size of the training corpora needed, or do you think that these models can be adapted to learn on a lot less?
Yeah, so you're completely right about the scale. So, as recently as the models on the left of my column, when it was sort of Elmo and Olmsted, you could say that wasn't an unreasonable amount of data to use relative to humans, 110 million. That's perhaps the amount of data that, at least in, first world countries, a kid might have seen by the age of 13. For what's happened more recently than that, I mean, clearly we're at a stage now where there's sort of about 2 orders of magnitude more data than human beings get access to when they learn languages. So I think that absolutely says we're not done yet, that even though these models seem very clever, they're nowhere near as efficient and good at learning from limited data as human beings are. Though do realize that these models have one huge handicap that little humans don't have. These models are learning just from an enormous amount of text, where clearly grounding the environment in which a kid is learning gives the kid an enormous additional amount of information, which is hugely important to language acquisition. But that's another whole talk that I'm not talking about today.
Okay, thank you.
All right, thank you. We now have a question from Samer Noor Adine. So Samer, can you unmute yourself, or can somebody unmute Samer?
Hello, can you hear me?
Yeah, we can hear you. Go ahead.
Chris, thank you for a great talk. I wanted to ask whether there's evidence that BERT is using the trees that's encoded in the latent space, or whether it's possible that it's actually learning them as an artifact and like you're uncovering them because you're looking for them.
So that's a good question. I think that that's something that, more work can be done on still. I mean, I think it's not 100% clear. I think what the answer is that it goes like this, that for the actual language modeling task of predicting words, I believe it is making use of this syntactic structure quite successfully. And you see that in its ability to do things like long distance agreement very well, I think it's fairly clear it's making use of the fact that it knows about what's the subject of what. Something that's been studied quite a bit recently is when you fine tune the models for a particular task like question answering, it actually seems like, even though that gives you a good supervised model for question answering, it seems like it's actually very destructive of the linguistic fine structure of the model. So commonly the output of those fine-tuned models seems to have lost a lot of the fine linguistic ability that the pure language model had.
Thank you.
All right, thanks. We have just about 2.5 minutes left. Briar Stefjella, can you ask your question quickly?
Yeah. So in your work on the uncovering the syntax tree from the model, you use the minimum spanning tree and recover that. My question is, what might be hidden, not just looking at the minimum spanning tree, but the other aspects of distance when you convert, the pen tree bank tree into the set of, the distance matrix.
Yeah.
Are there hints about syntax hidden in there that we might gain insight from?
Well, so yeah, I'm not sure I can give a perfect answer to your question, but I mean, certainly when we train this model, we're not only sort of predicting distance one kind of directly dominating nodes, we're actually trying to predict all distances, and that actually works better, and we're able to predict all distances well. So we can also sort of tell which words are, distance 3 apart in the syntax tree. There are then a lot of finer questions of, well, what kinds of other syntactic structure could you get out of this? I mean, could you detect C command relationships or something like that? Can you detect agreement relationships? Don't have full answers to that. I suspect some of those things you can, and even something like the co-reference example, that's more of a semantic pragmatic phenomena, but it illustrates that there's quite a bit of other structure in the representations.
All right, thanks. So we actually have like 1 minute left. Why don't you stop sharing? And while Elsie is getting started with her sharing, I'm going to let Roger Levy ask his question. But it's got to be.
Hi, Chris. Thanks so much. Hi, Chris. Good to see you, and thanks for the great overview talk. This is a super open-ended question. So like you, I've been sort of amazed at how sophisticated the knowledge and performance is of large models with high capacity trained on text alone. And I just, at a very high level, what strikes you as sort of the most human-like features of that success within these models, and the least human-like features of that success?
Okay, yeah, that's a big and difficult question. I mean, for the most human-like, I mean, in some sense, I find it hard to go past just this language model generation of, look, this thing can tell a story. I mean, that the fact that it's got such broad command of language, not just sort of knowing some facts about syntax and grammaticality, but is able to put together, connected, coherent text that develops a story. I mean, I think that sort of broad language competence is in some sense the most amazing thing. For the least human-like, I mean, we sort of touched on those before. I mean, although sort of this is an amazing proof of linguistic structure discovery from a big corpus of texts, it's not clear how much it has to do with human beings. I mean, human language learning is clearly extremely different in a grounded environment, and possible from certainly a lot less linguistic data, though we can debate how much data you're getting from the environment at the same time. So, it seems like you might need extremely different methods to succeed there. So, one big direction to head is just in general, how can we build neural methods that can learn more with less data? And lots of people are now working on that in areas like meta learning. But another area that's still, relatively speaking, is in its infancy, is actually doing grounded language learning. And that's obviously an exciting area.
Great, thanks.
Yeah, all right. Thank you so much, Chris. That was a really exciting talk. Let's everybody thank Chris. And unfortunately, there were some other questions, but I'm going to ask everybody else to just email Chris or put them on the website. There's a place to put a discussion, like there's a link you can follow there. And I'm now going to turn to the next talk in the session by Elsie Kaiser and Patrick George Gross. Take it away, Elsie.
Thank you, Jennifer. Yeah, so I'll be talking about anaphoric dependencies in the digital age on the relation between emoji and text. And this is joint work with Patrick Gross, who is also here. So any hard questions, you can ask him. I'm just kidding. Okay, so we're all familiar with emoji, I presume. These little icons and faces that we can use in digital communication. I've given here the top 10 emoji used on Twitter in 2020. We can perhaps draw some conclusions about how this past year made everybody feel. But now, regardless of how we feel about the linguistic status of emoji, presumably when we see them, we build some kind of link between emoji and the text that it's occurring with. So one could think of emoji as providing a new window into thinking about dependency formation. And we propose that there's at least 2 types of emoji text dependencies, crucially depending on whether we're dealing with face emoji or action emoji. And you'll see this is still very much work in progress, so we're very excited to hear your comments, criticisms, and feedback. It'll be super helpful. As I said, we like to propose that we should think about face and action emoji as being similar but different. So they both involve anaphoric dependencies, we suggest. They can be linked to prior linguistic context, but in different ways, such that face emoji linked to an experiencer, often the first person author or texter, akin to, we'll suggest, expressives in language, words like wow or yay. And action emoji, on the other hand, are interpreted based on principles of discourse coherence, akin to what we see with third-person pronouns. Now, let me just define a bit more precisely how we're using these terms. So with face emoji, we're talking about these yellow faces, and we're focusing on ones that have a clear effective meaning. There's a really intriguing question about whether face emoji should be viewed as part of a broader class of effective emoji, including thumbs up and a heart and so on. We'll come back to that at the end. Now, activity emoji are ones that look like objects or people, like the soccer ball or the surfer, and they describe an activity or property. I'm giving you some examples there at the bottom. Crucially, there's various emojis that are neither face nor action emoji, like the weather emoji and animals and so on. So we'll put those aside for now. And you might be wondering about emoji as an object of study. There's actually been a recent kind of burst of work on emoji from a variety of different perspectives. I've only mentioned a small sample of the work here on the slide, but admittedly, they are a human-created artifact, right? They have their roots in the emoticons of the 80s, and the first emoji keyboard on, I guess, like iPhones and so on came about 10 years ago. But we think that given that they're created by humans and used by humans in very particular ways, they can, we think, yield insight into how our minds work and how we communicate. And indeed, by some estimates in 2020, over 10 billion emoji were sent every day. So despite their recency, they're highly prevalent, which suggests that they reflect some type of communicative need. Now, one observation to make here at the beginning is that if we look at the frequency of emoji, we see a very clear pattern. This is a screenshot from Emoji Tracker, which gives you a real-time reflection of which emoji are most frequent on Twitter at a particular point in time. And if you look at the top there, you'll see that face emoji are very frequent, perhaps or presumably linked to the fact that faces are privileged in human cognition, as are emotions. So face emoji are used more than action emoji. And we can keep that in mind as we go through the talk. We'll be talking about the link between language and emoji, but we are not saying that emoji are language. Rather, our current thinking is that they're both modulated by, they tap into human cognition, broadly construed, but we're very happy to talk more about the relations between these different pieces. Now let's come back to the claim I mentioned at the beginning that both face emoji and action emoji are anaphoric, but in different ways. So we're going to test the idea that face emoji are like expressives, like wow or yay, that they by default express emotions of the first person speaker. Typically that person has the relevant experience, but can sometimes also shift to being kind of glomming onto a salient experiencer in the linguistic context. On the other hand, action emoji we propose are interpreted based on principles of discourse coherence, relations like explanation, elaboration, narration, in line with what we see with third-person pronouns. Let me now briefly say a few more words about these two types of linguistic elements before we come back to emoji. So if we think about expressives like wow, these typically convey the mental state of whoever's the speaker, in this case, Kelsey, who is amazed that I was actually on time. So the third-person pronoun points to a referent in the discourse context or in the world, but expressives point to somebody's mental state. And there's a lot of linguistic work showing that these types of expressions that convey someone's opinion or feelings are by default anchored to the first person speaker. I've given a bunch of examples here in A through D. So if I say she's amazing, that reflects my opinion. So it's anchored to the speaker. I'm using the subscript here to indicate whose opinion the adjective or the expressive reflects, typically the speaker. However, there's also some earlier work from my lab that these types of subjective expressions can also shift to expressing the views of another experience or argument if it's present in the linguistic context. So in something like E, David listened to John, he was wonderful. Wonderful could be my opinion as the speaker, or wonderful could reflect David's opinion. And we showed this in some prior work. But crucially, these expressives like wow or subjective adjectives like fun typically glom onto an experiencer, either the speaker or a linguistically expressed thematic role experiencer. Now let's think more about third-person pronouns. I probably don't need to say much about pronouns for this audience. There's a lot of work showing that they're guided by discourse coherence. So the large work on implicit causality, for example, looking at stimulus experiencer and experiencer stimulus verbs like annoyed and admired, shows that pronouns prefer to refer to the stimulus in these explanation relations, like I've shown in A and B. There is also other work showing that pronouns prefer salient topical reference. In English, this is often the subject. Now, today we're going to assume that both factors are at play. We'll be talking both about the stimulus thematic role and about subject. So we're not trying to disentangle these two views today. We'll see both are actually going to be at play. So in sum, what's relevant for now is this finding that third-person pronouns like topical reference, and with these explanation relations with stimulus experiencer verbs, they like to glom onto the stimulus. So far, we've just been talking about language. Now let's come back to our thinking about emoji. We propose that face emoji pattern like expressives in glomming onto the experiencer, whereas action emoji pattern more like third-person pronouns in going for topical reference, and in these particular contexts, the stimulus argument. So this is the hypothesis we're going to be testing, that they're both anaphoric, but in different ways, like I just mentioned. Now, we ran one experiment on this very simple study. People saw little text message snippets like that, like you can see here, and they were asked to fill in the blank. The emoji provides information about Daniel, Aaron, the sender. We did this with both action emoji and face emoji, and then we realized that actually the wording we were using for the face emoji was really vague, and I can discuss more about that if you'd like. And then we reran the same exact experiment, same stimuli, new participants, where we changed the wording for the face emoji. So now for the face emoji, people were being asked, the emoji expresses the feelings, emotions of the subject, the object, the sender. I'll be talking about experiment 2 in the interest of time. I'm happy to show you the data for experiment 1. It's also in the abstract. They basically replicate each other. It's just that things are clearer for experiment 2 once we made the wording more specific. But I'm happy to talk about that. So in this experiment, we had 56 participants answering questions about these little text messages. The emoji were always message final, which is a very frequent position. And we used actually images that we showed people to avoid any type of changes across operating systems. And now to think about this experiencer stimulus asymmetry that we're proposing, right? Because we think face emoji glom onto experiencers, action emoji glom onto the stimulus. We used psych verbs of these two types, stimulus experiencer and experiencer stimulus, to test whether this hypothesis is correct. So these verbs, things like annoyed and admired, they both have a stimulus and an experiencer. They differ simply in whether it's in the object position or the subject position. So these verbs are a great tool to probe our hypothesis about face emoji being linked to experiencers, like expressives in language, and action emoji being interpreted as providing information about the stimulus, like third-person pronouns. So here is part of our design. Got the verb types on the rows and the action and face emoji in the columns. We chose the face emoji to express positive or negative affect. And crucially, we on purpose tried to make them as ambiguous as possible because we wanted to see whether people would interpret them as subject, object, or author, right? So we tried to make them super ambiguous between all three options. And this is also why they matched the valence of the verb. The action emoji represented objects related to actions or properties, along what I mentioned earlier. So far, I've been talking a lot about experiencers and stimuli. But remember, we also know from prior work that expressives have a default speaker preference, it's been claimed, and third-person pronouns we know also like topical reference. So we also had a secondary manipulation looking at transfer verbs to kind of probe these ideas to see if they extend to the emoji classes as well. So we had action verbs like brought, Abigail brought dessert to Emily, transfer verbs like brought, occurring with action emoji and face emoji. And now these transfer verbs have no experiencer or stimulus argument linguistically encoded. Again, the face emoji were chosen to be maximally ambiguous, the best we could, and action emoji with transfer verbs depicted the transferred object. We also manipulated aspect. Brought was bringing. Given some prior linguistic work on this, we actually found no effect of aspect, which was very surprising. Well, intriguing, and I'm glad to discuss that if you would like during the Q&A. So here is kind of our admittedly somewhat Frankensteinian design, where we have action emoji and face emoji, and we tested transfer verbs like I just mentioned to you, and to the SE and ES verbs here on the bottom. So let me briefly go over the predictions. I'll first talk about face emoji for both verb types and then action emoji for both verb types. So for face emoji with stimulus experiencer verbs, as shown here, we crucially predict that if they are like expressives in the linguistic domain, things like wow and yay, or subjective adjectives like fun and tasty, the face emoji should, at least in some contexts, reveal the default preference to kind of be interpreted as conveying information about the first person sender of the message, the author of the text message. Also, we predict that they would prefer to be linked to the experiencer argument if it's linguistically present, as shown in these sentences here. And I've given you a reminder of the task there at the top. Now, as for face emoji with transfer verbs, so here, remember, we have no experiencer argument present. So here's where we were thinking that we might be able to detect a preference for the author of the message, that the face emoji would express the feelings or emotions of the sender, the author of the message. As for action emoji, let's again first consider the stimulus experiencer verbs. If action emoji show discourse coherence effects similar to what we've seen in prior work with third-person pronouns, we expect that they would be interpreted as providing information about the stimulus argument, shown here in red, Richie with annoyed, Aaron with admires, regardless whether it's the subject or the object. So the key thing, or one key thing to keep in mind, is that the action emoji, we predict the stimulus preference, and the face emoji, we predict an experiencer preference. Now, as for action emoji with transfer verbs, like brought, here there's no stimulus argument present. So we were thinking that this might be a context where we might perhaps observe a preference for the subject of the sentence, building on prior work with pronouns. I have a question mark here because it kind of gets a bit more complex in the linguistic work, so I'm somewhat oversimplifying, but we thought maybe people might predict, they might opt for the action emoji providing information about the subject.
Okay, Elsie, 5 minutes.
Thank you. Now let's look at the data for transfer verbs. We'll start with that first. So we want to see, do face emoji glom onto the author? Do they express something about the emotions of the author? And do action emoji glom onto the subject? Now in these graphs, I have action emoji on the left, face emoji on the right. The proportion of choices of author, subject, or object is given on the y-axis. And if we look at the face emoji, the gray bar is the tallest, so they do indeed have a higher than chance probability of being interpreted as expressing the emotions of the author of the message, in line what we might expect based on linguistics. For action emoji, we have a really tall green bar. This is the subject. So there's a really strong preference to interpret them as providing information about the subject. which is similar but not quite the same as third-person pronouns. Third-person pronouns don't show quite such a strong preference, so I'm happy to discuss that. In all these graphs, I'm showing the chance level, like 0.333 with the dotted line, and a star just shows significantly different from chance. So that was the transfer verbs. Now let's get to the key stimulus experiencer asymmetry to see, do face emoji glom onto the experiencer? Do action emoji glom onto the stimulus? Here, the graphs are plotted a little bit differently to make it easier to follow. We're going to show experiencer in blue, regardless of its grammatical role, and the stimulus argument in red, regardless of its grammatical role. With SE verbs, the tallest bar is the blue bar for the experiencer, it's the object. And with ES verbs, again, the tallest bar is the experiencer. So we find that face emoji do tend to be interpreted as expressing emotions of the linguistically expressed experiencer argument. So regardless of verb type, people go much more for the experiencer, the blue bar, than for the stimulus. And I'm happy to talk more about the subject-object asymmetry because we see subject being a better choice. Now let's think about the predictions for action emoji with the same verb class. Because remember here, the question is, will they glom onto the stimulus? Because that's what pronouns would do. So here, drum roll, we need to see, will we see the switch from experiencer to stimulus? And indeed we do. So with both verb types, the tallest bar is a red bar. That's the stimulus argument. So action emoji tend to be interpreted as providing information about the stimulus. Again, intriguingly, the effect is stronger with subjects than with objects. But overall, this is very much what we see with third-person pronouns that show effects of discourse coherence.
Elsie, 2 minutes.
So summing up, the hypothesis we were testing is that both types of emoji can be anaphoric, linked to prior context, but crucially in different ways. And indeed, we think our data supports this idea that face emoji are like expressives in that they glom onto a linguistic experiencer if it's present. And if there's no linguistic experiencer present, like with transfer verbs, then they are interpreted as being about the sender. Action emoji, on the other hand, seem to be like third-person pronouns, sensitive to discourse coherence, as well as topicality, as we saw with the SE verbs, ES verbs, and the transfer verbs. Quick disclaimer, there's obviously also other factors at play. You can't just stick any emoji after stimulus experiencer verb and have it make sense. There's limits to our discourse inferencing that we can do. Same types of things happen in language, as Hobbes noted, and also Ajurowski commented on. So we see parallels here as well. And there's a lot of, we think, interesting open questions, next steps that we're thinking about. Are face emoji a subset of a broader class of affective emoji? So are they different because they're faces? We know faces are privileged human cognition. Are they different because they're affective, linked to emotions? We also have a lot of follow-ups we're working on, playing around with the match between the emoji and the valence in the sentence, different response options, other emoji classes, and of course, the big question that this is kind of all feeding into, the idea of how can we link this to psycholinguistic models of anaphora resolution, dependency formation? Like, can those models help us think about this different piece, this emoji piece? We've also been doing some formal semantic work on this. We have a proceedings paper that's available online. If anybody's interested, we try to flesh out more some of the coherence relation reasoning there. Let me just then conclude by saying that hopefully I've given you some initial experimental evidence for two types of emoji text relations reflected by action emoji and face emoji. And we think this fits with our proposal that both types are anaphoric, but crucially in different ways that echo what we have seen in language before with expressives, as well as with third-person pronouns. So I'm going to stop there. Thank you for your attention. And also thank Prim, who was crucial in helping us develop the stimuli, and thank the NSF for funding.
All right, thank you, Elsie. Everybody clapping. Okay, we've got about 9.5 minutes for questions. And the first question is from Anna Katakina, and she's asked that I read it. She's asking, what were your predictions for the aspect manipulation?
Oh, Yes, great question. So here we were expecting for the, oh, I don't know why that final bullet. Here we go. So there's prior work on aspect by various people, including Kaler et al., where they were looking at things like John was handing a book or John handed a book. And they found that the source was chosen more with imperfective aspect, like John was handing a book. People talk more about John, but in John handed a book to Bob, relatively speaking, Bob gets considered more when it's perfective, like handed. So we were curious to see, even though we didn't have pronouns like the prior work did, we had these transferred objects as our emoji. We were curious to see if there would be some echo of this source goal and like this end state bias in particular with the perfective. But here's kind of a quick graph. You can see they actually look extremely similar. So we found no effective aspect. We think it's because they're not the same as pronouns. They're similar, but they're not the same. And it's more about the coherence than about the particular referential element.
Wonderful, thank you. The second question is from Bethany Gardner.
Hi, can you hear?
Yes.
Great. This is really cool. And so the first thought I had when looking at your stimuli is that I very rarely see object and action emoji used that way, where you have a sentence and then you put a noun or an action emoji at the end to like emphasize to talk like related to what you were talking about. At least this is like for me. I'm in my 20s. I never see anyone do that. The version I do see is in things like Slack and Discord, where you can add a custom reaction. And so the speaker says something like, "I'm bringing cake to the party tonight," and then people will respond to the message with like cake emojis. It's like a more complex version of liking the message. And I'm curious to see like what you think, like usages like that, how those fit into this theory, because like those are actually like generally the versions I see that are much more frequent.
Yeah, no, thank you. These are great points. One thing I'm going to kind of point to is this paper, the Gross-Kaiser-Pierini, which Patrick has on his website, and mine's going to be there shortly. We actually we look a lot at Twitter corpus data. So there are a lot of corpus examples, because crucially, that's something that we want to make sure we're talking about real examples. So there's a bunch of corpus examples in that paper. It's also worth noting, as I said in the beginning, that the face emoji are much more frequent. So I think I'm happy to say that, that the action emoji type things are kind of a different animal, I think. People still do use them quite a lot, as a Twitter search will reveal. The face emoji are much more common. And I do actually think we have various examples like this that we've come across quite a bit. But I'm a huge believer in corpus data. So we kind of have this parallel to Etcher Checker looking at corpus examples a lot. The final point, where I'm just about to, or we're currently designing a study looking at reactions in line with what you were saying. When somebody posts something and then other people react to it in different paradigms, because I think that gets into related but distinct issues. So I'm very interested in getting a better handle on that.
Cool. Yeah, the place where you see these type of custom reactions are also the places where it's harder to get open corpus data. So that kind of makes sense.
Yeah. Thank you.
All right, cool, thanks. The next question is from Jianghua Cho, and I'm going to read this one too. It says, "Thank you for the interesting talk. I'm wondering whether you plan to see how emojis are actually used on SNS, e.g. Twitter, in the future, and whether you think you'll find similar patterns." Actually, I think you just answered that with your corpus data.
Yeah. So
this was posted earlier before you answered that one, but yeah. Do you want to say anything else about that?
I think I'll just emphasize, and Patrick can also speak to this. Patrick is like the Twitter search wizard. We're super committed to corpus data, because one of the key things we want to make sure is we're not looking at things that don't happen. And on a quick side note, there's huge generational changes, right? So the way that I text is not the way Prim texts. So we're also doing this work very much in consultation with people of different age brackets to get a sense of that. So definitely that's a very big piece of all this. Thank you.
Cool, thanks. The next question is from Claire Patterson, and I'm going to read this one too. Given that the context of your experiment was direct messages, did you consider giving an option of receiver, i.e. the emoji expresses supposed emotions of the receiver for the face emoji?
Not in this study, but we have thought about that in other contexts. And I think that's something that happens in language with expressives. If you have questions, for example, you can shift to the addressee. Like if I say, you know, was the cake tasty? I'm asking you for your opinion. So we haven't done that yet, but we're definitely thinking about it.
Mm-hmm. Cool. And Jack Dempsey, UIOC, also is asking me to read this one. It says, do you think results might be different if the question answering were a free response, like who does the emoji describe? It might be hard to elicit sender of message responses, but maybe something to think about. Do you think forced choice might bias towards choosing something other than the sender?
That's a great question. We're going to do a follow-up where you can choose multiple responses, like, you know, choose all that apply. We've done that in other work, and it's been informative. I think some kind of open response would also be super helpful. Might be hard to analyze, but it's definitely something that we're going to look into. Interestingly, if we think that there could be a sender bias, we actually saw lots of people opting for not for the author. So they were happy to shift away from the sender in our data.
Yeah. Cool. The next question is from Emily Atkinson, who's going to ask it live. Emily?
Yes, can you hear me? We good? So you sort of started talking about this at the end, Elsie, where you mentioned that you can't just sort of pair any action emoji with any verb situation. And I was wondering, because I felt that it felt very much like I had an immediate intuition about the annoyed case, but less of an immediate one about the admired case. So of the examples that you gave. So I was just wondering if you had looked at the preferences for the individual items and if maybe there was sort of more variability in the object experience or cases, and that's why you were finding sort of less strong preferences in those cases.
Oh, I see. Yeah, great question. Because we did find, we haven't looked at that super well, it is true that the object experiencer is weaker than the subject. I thought that is probably due to subjects being more prominent. But we could think about this. Here, I just put up, Patrick generated this the other day. This is kind of just random emojis paired with verbs, because it seems like there are pretty strong effects kind of no matter what you choose. Our brains are really good at trying to make things coherent. But it is definitely something to think about, like what underlies potentially the finding that we had repeatedly, that the objects, like here, the object, it's still preferred way above chance, but it's weaker. So I think the reason underlying that is a very good question.
Cool. Yeah, I think it's just something about like the drum was very obviously something that one could use to annoy someone. And it just took me longer to get the connection between like the metal and the admires. So yeah, so that's why I was wondering about individual cases.
Oh, I see. Well, there also, I mean, we had a range of stuff across our items. But I think we can take a look at these. And I think like here, you know, you can probably, for all of these, we can probably think, you know, Daniel admires Aaron because Daniel plays tennis really well. No, Aaron plays tennis well. Richie annoyed Adrian because Richie was throwing a tennis ball around. So, I mean, we seem to be pretty good at coming up with these, but I definitely agree that there's more work and more replication to be done.
Cool. Thanks, Elsie.
Thank you.
All right. Thank you, everybody, very much. We are just about out of time, so let's give Elsie a big thank you. So that's a clapping for everybody there. And so, John, sorry, I didn't understand your answer to my question. When you say,
yeah, I was going to jump in and just say that we will have just a 15-minute break here, and we'll try to start at the scheduled time of 4:45.
Wonderful. Okay, thank you. All right, thanks to the speakers, and we'll see you back at